It is a great pleasure to have Professor Anupam Gupta from New York University visit us. Anupam Gupta is a professor of computer science department in the Courant Institute of Mathematical Sciences at New York University. Until recently, he was at Carnegie Mellon University. He did his PhD work at UC Berkeley and his postdoc work at Cornell and Lucent Bell Labs. Anupam's research interests are broadly in the design and analysis of algorithms, primarily in algorithms for optimization in the face of uncertainty, in approximation algorithms for NP-hard optimization problems, and in understanding the algorithmic properties of metric spaces. He is an ACM Fellow and a recipient of the Alfred P. Sloan Research Fellowship, the NSF Career Award, and CMU's Herb Simon Award for Teaching Excellence. So over to you, Anupam.
Thanks, Devesh. Thanks, everybody, and thanks for having me here. This is like the mid-afternoon session talk, right? So I would like this if it were interactive and stuff like that. Please ask questions. I have a bunch of material, but I don't have to cover it all. I would rather you understand what's going on. So the talk's going to be about online algorithms and going beyond the worst case. And in fact, the setup that Hamid, those of you who were at Hamid's talk, the setup that he gave is a perfect launching point for me as well, right? Because he was talking about how to go between the worst case and the distributional case, and pretty much that's exactly where I want to be. Now, the perspective is slightly different because those of you who've taken an algorithms class, you know about this, that the way we study algorithms typically is to understand its worst case behavior. Now, how does this algorithm do on the worst possible input? And so we are looking for the adversarial example, so to speak, right? And there's very good reasons to study the worst case analysis of these algorithms, as you know, and maybe I'll just say these so that we are on the same page, and then from this point onwards we can move ahead. And the first, perhaps the simplest reason is its robustness. I know exactly how it's going to behave on each and every input. There are no surprises. Dijkstra's algorithm takes, whatever, m log n time on every graph with m edges and n vertices. And there are no surprises out there. And, this is an amazing property. The robustness is awesome. There's other reasons as well. It's a widely applicable model. You can use this in a variety of applications, even ones where there isn't a clear distribution model. And perhaps the third one, which is often less emphasized, is we would not be studying the worst case analysis of algorithms if we didn't have good algorithms. So we are lucky. Nature has been very good to us. It's given us algorithms which actually do really well, even in the worst case. So given that, it makes perfect sense for us to look at the worst case analysis of these algorithms. And maybe the last point is, it's a less contentious model. We don't have to worry about, what's the right base distribution? What's the underlying properties? What's the underlying structure? It's the worst case. It's the adversarial example for this particular algorithm. And of course, the downsides are exactly what we talked about earlier. The downsides are simply that it's overly conservative. It's perhaps pessimistic. And it's insensitive to the data model, to the predictions. And these are it's the same line. You'll see the same line later on. The more things change, the more they remain the same. You'll see the same line where one end will be adversarial and the other will be distributional, and then we'll try to bridge between the two. So that's what we're going to do. The difference is really going to be in the choice of problems and, to some extent, the techniques. So you'll see much more combinatorial techniques in my talk. Which is not to say that both these areas, we do a mix of combinatorial and continuous techniques. And it's just the choice of the ones that we are showcasing today. That's the difference. Now, it's entirely coincidental that his talk was just before mine. Otherwise, we would have planned this together. Okay. So in any case, let me get to the motivation behind going beyond the worst case. And again, maybe one more slide of philosophizing, and then I'll get down to the details, the mathematics of it. The ideal situation, and when I talk to people, is like, I don't care about the worst case. I care about my instance. In some sense, I care about my case being my instance that I want to solve. I want to solve this as fast as possible. So, there's this tension between how do you figure out what my case is, what's the structure of the input. And so I would like to be worst case and best case in all cases. I would like algorithms to be really fine-grained in that sense, that algorithms should perform well in the worst case. They should perform well. They should perform even better on better structured inputs. They should perform better when we know more about the input distribution. The more we know, the better we should do. It should be as simple as that. Okay? So I'm going to use these two terms. Worst case is very clear. Worst case is when the data is unpredictable. I would like to understand the adversarial examples, how bad things can be. And to some extent, I want to say, best case, it's within quotes because it's not a formal definition. I would like to understand the efficiency when the data follows anticipated patterns. Okay? So really, I want to emphasize the two terms out there, robustness versus efficiency. The robustness is the worst case. Efficiency, I would like to think of as the best case. And the rest of the talk will be looking at a few examples, a few ideas and techniques that come up in the context of an area called online algorithms, where I work a lot. Okay? So I'm going to basically pick up 2 or 3 problems, and I'm going to investigate them beyond the worst case. So this will introduce a few models, and this will introduce a few techniques. Okay, good. So that's the main goal. Okay, so online algorithms, and actually, I'm tempted to stand. I'm tempted to go down, but I don't know whether that's a good. Let me try it. Okay, and don't mind me if I pace around a little bit. Okay. So what are online algorithms? Online algorithms are algorithms where the input comes one by one. You see a sequence of requests. When you see a request, you have to handle it right then and there. You don't know what's going to come in the future. Okay. So these are, let's say, and each decision I take, when I serve a request, I make a decision, and that incurs the cost. And I want to minimize the total cost I pay. Okay? All this is vague, so let me make it this precise. Ignore this thing. Okay? Just look at those points out there. Okay? They're the green root vertex, and they're the metric space. I tell you now, connect that red vertex to the root. You incur some cost. Now I give you another red vertex, connect it. You always want to, in this problem, the goal is to make sure that the red vertices are always connected to the root. They form one connected component. Okay? A new vertex comes in, you want to connect it to the root somehow or the other. You'll pay some amount of money. Another vertex, you can connect it whichever way. You can use other intermediate blue vertices, but you want to make sure that the red guys form a connected component. Okay? You're paying for the edges that you're adding in. You want to minimize the total cost. Does this problem make sense? The cost is the cost of an edge is the length of the edge. It's the distance. Okay? This problem makes sense? Questions about this problem? I'm going to tell you about 3 problems, and we'll investigate these 3 problems in some detail. Okay? This is called online Steiner tree, and the Steiner tree is because I can't point at these things. Maybe it is the right move to be. The blue vertex out there, I'm allowed to use vertices which are not the required vertices, the red vertices. I'm allowed to use blue vertices as well in connecting up the red guys. Okay? Good. Let's say they're there at time 0. The entire metric space is known to us. And just some of these vertices light up and say, oh, connect me to the root. Now I have to connect them to the component. Good. Other clarifications? Good. Okay. What?
Am I allowed some preprocessing on the graph?
Sure. But I don't know which vertices are going to light up. So I can do all the preprocessing, but what can I do? I can just measure all the distances. That's pretty much it, right? Good. Okay. What's my measure of goodness? My measure of goodness is my cost, which is the numerator out here, divided by the optimal cost in hindsight. I pay something every step. I sum that up. That's my total cost. Then at the end of the day, I can look back and say, oh, those 4 vertices came. What was the best way? Had I known the entire set up front, what's the best way I should have done it? That's the denominator.
So in here, the instance also defines the initial 2 points and then the sequence of the red points.
Absolutely. Okay. So vertices can keep coming over time. You look at this and you'll say, maybe I should have connected it some other way. That's the denominator. The numerator is what you paid. The ratio is at least 1. You want to minimize this ratio. Okay? And the adversary is trying to find the instance that maximizes the gap between the two. This is called the competitive ratio. Does this make sense? Your cost divided by the optimal cost. I'm sorry?
Do you fix the instance size?
It depends. So you could say, what's this ratio as a function of the input size, the instance size. Okay? You want to minimize this competitive ratio. Make sense? Good. Let me give you a different problem. So in online algorithms, typically we don't worry about the time complexity. But once we know the right ratio, we can try to say what's the most efficient algorithm that achieves this. Absolutely. I'm sorry? So the blue nodes are just defining the metric space. When a node lights up, it becomes red. It needs to be connected to the root. So it starts off like this. The green node is the root. When a red node comes, it needs to be connected. Another red node comes, it needs to be connected. Does this make sense? Okay, good. Here's a different problem. It's called set cover. I give you a bunch of elements, and I give you a bunch of sets which contain some of these elements. So this is a set system, a bunch of elements and a bunch of sets, bunch of subsets. Elements arrive online. When an element arrives, you have to pick a set that covers it. There must be at least one set in your hand which covers this element. So maybe this element comes. You have those 3 sets. You have to pick one of these sets to cover it. Maybe another element comes. Maybe you need to pick another set to cover it. A third element comes. You need to pick another set to cover it. In this case, it happened that you picked all 3 sets. What's the best thing you could have done in hindsight? Pick S3. So the ratio out here was 3. So in general, you are picking some number of sets. You compare this to the best number of sets you could have picked in hindsight. Okay? This is online set cover. Yes?
For the previous problem, is the metric space required?
So if you allow yourself to connect via the intermediate nodes, you don't need the metric space. It just makes your life easier to think about. Totally. Thank you. Okay? Let me give you a third problem. And this third problem is actually very easy. So there won't be any. N people arrive over time. When a person arrives, you see their value. You want to pick the person with the maximum value. However, when you pick a person, you can't unpick them. Okay? In general, you can pick at most k people, and you sum up their values. You want to maximize the sum of the picked people. So you want to pick k options out of the n options coming to maximize the value. Okay? And in this case, you'll have to change the definition slightly because it's a maximization problem and not a minimization problem. So you compare your value to the optimal value. This number is less than 1. You're trying to maximize this. and the adversary is trying to minimize it. Okay? Good. 3 problems. We'll just study these 3 problems. Okay. Now, these problems have been studied in the offline setting, where the entire input is given to you, and also in the online setting, where you have to make decisions one by one. Okay? And you'll see there's a gap between them. If the entire input is given to you, in polynomial time, and here I'm a theorist, right? So I talk about polynomial time as my yardstick. In polynomial time, I can get a 1.3 approximation to the best standard tree. But if the input comes one by one, I can't do better than log n compared to the best standard tree. Okay? And you see the price we pay for making decisions online. Okay? Maybe I'll talk a little more about these things as we go along. In set cover, in polynomial time, you can get a log approximation. The greedy algorithm is a great algorithm. But it turns out that in the online setting, you pay log square. Not important why right now. Okay? Again, you pay a price for being in the online setting. Okay. Max finding in the offline setting is trivial. You can find the max, or even the max top k people, right? Linear time. But in the online setting, what are you going to do? You have to pick k people. Just forget k. K equals 1. I'm showing you numbers one by one. You have to pick the max. You have no hope. You're basically doing random guessing. The probability of being correct is 1 over n. So in the online setting, you're basically dead. Question?
Just to clarify, you compare efficient polynomial offline setting with arbitrary online setting, or also efficient?
Good. So it's arbitrary online. And yeah. Okay. So these are tight with some caveats sometimes. Sometimes I might want it to be deterministic, things like this. But these are essentially tight.
For set cover, n is the number of points that you need to cover, or does the set system also?
Good. So really, the log square n is log m log n, but I'm imagining m and n are polynomially related for the time being. Good. So the thing is, the point I want to make is one that you've already sort of observed, is that in the online setting, you pay a price. Yeah?
Average case or
Worst
worst case?
case. Everything's worst case so far. So now the question comes, can we go beyond the worst case? Thank you. That was an excellent question. So what I'm going to do is basically I'm going to make a third column out there, and I'm going to look at various worst case models. And really the sort of question is, how do I define a non-worst case model? And there'll be various definitions, and we'll explore them a little bit. Okay? All good? Yes?
So the knowledge of n is known what at day 1?
The knowledge of n for, let's say the knowledge of n is known from day 1. Let's say. Make our life easier. In some cases, we might get away without it, but let's say n is not. Perfect. Other clarifications? Yes?
In the max k-find problem, the ratio is of the values.
The sum of the values.
Why is the ratio then even 1 by n? Because it would be arbitrary. You pick a very small value and
Good. So here is an algorithm which will give you 1 by n. I know n. Pick a random number between 1 and n. Pick that person. So in expectation, I'm getting 1 over n of the sum. Sorry, I'm getting, the average of the sum, which is at least the max. Good. So I can get 1 by n, and essentially there's nothing better I can do. Maybe all the values on one person. I'm sorry? So we'll see the worst case example in just a moment. Yeah. These are random. I'm not worrying about randomized versus deterministic. Yeah. We have enough parameters to worry about. Okay. So what am I going to do? So first I'm going to talk about some worst case, some beyond worst case models. We'll look at some of these problems. Then I'll talk about, we shouldn't overfit to these models, and this goes, you'll see the analogy with Hamid's talk. And then maybe I'll talk a little bit about predictions as well. Of course, chances are I won't get to get through all of this, but that's fine. Catch me later on, we'll talk more. Okay, good. So here's the chart again. Let's talk about max K finding. And in fact, these questions I'm going to talk about, these are all 50-year-old algorithms, 50-year-old problems. And, at least we'll set the stage. Okay. So in fact, max 1 finding. There are n numbers. I'm going to show you one by one. You have to pick the max. Or you have to maximize the value of the element you pick. Okay? So in the offline setting, in the online setting, you're pretty much dead. And here's the example, right? I show you one number. Should you pick this? Maybe not. I don't know. Then I show you a number. And let's just imagine that each of these numbers is much, much bigger than the other one. Imagine this is like a log scale or something like this. So the instance I'll give you is I'll give you an increasing sequence, and then it falls off the cliff. You should have picked that top guy. If you picked anybody else, you don't get much value. And where is that top guy? It's at a random location. So you have no hope except random guessing. In the worst case, you're pretty much dead. Okay. So how do people get around this thing? So what people do is they come up with a whole bunch of models, how to go beyond the worst case. And if you're interested in this kind of stuff, and I hope you will be at the end of this talk, or by the end of this talk, you should pick up this book that Tim Roughgarden put together. A bunch of us wrote survey articles about various beyond worst case models. And it's a fun book. I really enjoy it. So you can do various things. You can say, hey, maybe the values lie in some bounded range. Can we do better? What if the values are drawn from some distribution? Can we do better? What if the order in which these bad elements came, that order is not fixed? Can we do better? Etc. And each of these is going to, can we train a neural network to find patterns in our data and use that to give predictions? I had to throw in the neural network thing somewhere, right? It's a miracle of our times in some sense. Anyways, you can think of 40 different models in which you can cast max finding. I'm going to talk about a few of them. Okay, so let's talk about 2, which I'll talk about. I'll use these models as a springboard for better stuff. This is work that goes back to 1978, so about 50 years, 45 years right now. Items arrive online one by one. The ith item is drawn from distribution di. You know di. This is the assumption I'm making. Okay? You are allowed to pick one item, maximize the expected value of the item you pick. Okay? This, by the way, is called the profit model. You're because you're comparing yourself to a prophet who knows the future in some sense. Okay? But is the problem clear? Okay. What's an algorithm? So let me give you an algorithm. And this algorithm, actually, Krengel and Suchitsan gave an algorithm which is perfectly fine. But I'm going to give you an algorithm which is much more recent, but which I find very elegant. Okay? So here's an algorithm. I need to use the distribution somehow, right? So let's use it in the following way. Let's take one sample from each of the distributions. Okay? Let's look at the maximum of these samples. This is all in the pre-processing stage. Now, the first element is drawn from D1, the second from D2, and so on and so forth. Pick the first element, the first real value that lies above this threshold. This is my algorithm. Kind of sort of makes sense. I want to pick a high value item.
So I think
What's that?
Can I be unlucky?
So you might be unlucky in the sense that none of these values lie above the threshold. Just pick the last one. Yeah. Okay. So, algorithm clear? Okay. My claim is that this algorithm has expected value which is at least a quarter of the maximum real value. Actually, the correct answer is half, and this algorithm gives you a half, but I'm going to show you a quarter because the quarter analysis is 2 lines. We'll do it. Okay? So let's do the analysis. My claim is that the expected value of my algorithm is at least a quarter of the expected maximum. Okay? Okay. Remember, our algorithm, I took n samples, 1 from each distribution, and then the real values are there, 1 from each distribution. The Ri and Si have the same distribution, right? Okay. All right. Take these n numbers, take those n numbers, put them together, they form 2 n numbers. Sort them. Okay? What's the probability that W1 corresponds to a real number? Real element. It's 1/2. Because each Wi is Ri or Si. They're drawn from the same distribution, and you've kind of hidden whether it's an Ri or an Si. So the probability that W1, the highest guy in the sorted order, is real is 1/2. Conditioned on that, what's the probability that W2 is a sample? Now, if W2 and W1 were from the same distribution, then it's probability 1 that W2 is the sample. Otherwise, it's a random color. And if W2 is a sample, that will be the threshold because to pick W1. That gives you a quarter. Easy peasy. Okay? You can do a more sophisticated analysis, get 1/2, but that's for another day. Yeah?
What happens if instead of using the samples S1 to S2, you use the expectations of the expected values of the distribution?
If you use the expected values of the distributions, so are you going to use the highest expected value as a threshold?
Something like that.
Yeah. So let's change your algorithm slightly. Let's look at the max of the n samples, and look at the expected value of the max. Use that as a threshold. That's pretty good. So the bad example for your case is if there are, let's say, n distributions, IID, each of them comes up heads or comes up value 1 with probability 1/n, then your expectations are very low. But you do expect 1% to come up high. So you've got to be a little careful around that. Other questions? So you see, we use the distribution, and somehow the distributional information was very helpful in designing the algorithm. Okay? Good. Let me give you second model. Prophets and secretaries. I changed I should have changed the topic of the title of my talk to talk about prophet secretaries. So this is called the secretary model, and this goes back to even earlier to Flood in 49. Okay. There's no distribution. The adversary picks n values, but they appear to you in uniformly random order. Okay? You want to maximize the expected value. So how many of you have seen this problem already? Some number of you. Okay. So in any case, here's an algorithm that does pretty well. You have no idea about what the numbers look like, right? How should you figure out? You should sample. How should you sample? Just look at the first half of the elements as they come in. Look at the highest value you see in this first half. In the second half, pick anybody who is higher than this threshold. Okay? Claim. This algorithm is again a quarter competitive. It has a quarter of the optimal value of the highest value. And here is the one-line proof, right? The probability that the highest element comes in the second half is 1/2. Condition on that, the probability that the second highest element comes in the first half is at least 1/2. That's 1/4. And it's very similar to the previous proof. That's why I kept these two proofs. Okay. This algorithm, by the way, is not optimal. You should ignore the first 1/e, where e is the base of the natural logarithm, whatever, 2 points something, 2.7, right? You should ignore the first 1/e fraction of elements and then pick the best, and that gives you a 1/e competitive, and it's the best possible. There's various proofs of this. It's very cute. Some other time. What's that? Oh, is it in CLRS? Oh, awesome. CLRS is catching up. It's no, it's like the Wikipedia page for this has another proof for this as well. Oh, it's quite old. I'm dating myself. It's so, okay. Let me ignore this one for the time being. Okay. So I gave you two proofs, two models where you could get much better results if things were not in the worst case. Okay? So let me tell you a couple of other. You might think, oh, this was just, I was picking the maximum element, right? How hard can it be? But the ideas are very simple. They're generalizable. That's the beauty of simple ideas. You can generalize. Generalization bounds are something we learn in machine learning all the time, right? Occam's razor, keep it simple. Anyways, these simple ideas will generalize. I'll give you two examples. Okay. So let me remind you of the problem, and hopefully I haven't changed the colors, so I won't confuse you. So, there's a metric space. Not important whether it's a metric space. There's a root vertex, and now vertices turned red. If they turn red, you must connect them to the root. Okay? You must connect them to the root. You must make sure that the red guys all form a connected component with the root. Okay? So I did a greedy algorithm. It gave me these edges. But of course, if you look back, you say, well, no, you should have actually connected them all that way. So you paid a lot more than the greedy algorithm. That's your comparative ratio. And this example, if you just repeat, you just take this at many different scales, you can show a log gap. But let me not do that. I don't have that much time today. Okay. The worst case comparative ratio is log n. Okay. Actually, let me tell you why it's log n. I'll give you an example like this. I'll tell you connect the rightmost vertex to the leftmost vertex. You can either take the north path or you can take the south path. Suppose you took the south path. I'll say, no, you should have taken the north path, because I'm going to give you the midpoint of the north path. Again, you can take the north path or the south path. Again, maybe you took the south path. No, you should have taken the north path. Whichever way you went, you were wrong. And so basically, I can give you a sequence of vertices from left to right, so that if you had guessed correctly, you would have just bought this path, like this one out here. But you guessed incorrectly, so each time you paid a lot. If you formalize this idea, you get a gap of log n for n vertices.
Is the lower bound specific to a particular metric space? Or?
So the lower bound is showing that for this metric space, there exist instances where you'll do poorly. And since we are doing the worst case over all possible inputs, it's worst case over. You might say, oh, maybe a low dimensional instance is good. Even in 2 dimensions, you can get a log over log lower bound. Yeah, somehow not knowing the future is a big problem. So let me give you the same problem in the prophet model. Okay? There are going to be n requests. The first red vertex is going to be drawn, is going to be a random vertex from these blue guys from some distribution D1. There's some distribution, and if you don't want to keep these distributions in mind, just imagine uniform distribution. All of them are uniform. So the first red vertex is a uniform vertex. You want to connect it. The second vertex is, again, a uniform vertex you want to connect. Whatever. Okay. What's a good algorithm? You want to use the distribution somehow. How should we do it? Well, first step is clear. I have n distributions. Take one sample from each of the distributions. That's the least I can do. Okay? Now, what to do with these samples? Let's build a tree on them. Connect them to the root. So, there was the green guy. Okay, so I took samples. There are 6. N is 6 in this case. So I'm taking 6 samples, one from each distribution. These are my yellow vertices. Yellow is my samples. Got nothing to do with the guys I need to connect. This is just my pre-processing. Yeah, please. I'm sorry? No. There might be collisions. That's okay. In fact, you should always, for this talk, just think of the distributions as being uniform. Okay? I took, n samples. Let me build a tree connecting them up. Okay? Now, the actual requests arrive. When the request arrives, connect it to its closest previous point. Is the algorithm clear? And the algorithm should kind of make sense, right? I took a bunch of samples, I built a tree on them, but these samples look like the real points tomorrow. If I build a tree on them today, it should cost the same as if I were to build them tomorrow. Okay. Let me do the analysis. My claim is that this algorithm costs you no more than twice the minimum spanning tree on the real vertices. And this is where having a metric space helps, because the spanning tree and the best Steiner tree are within a factor of 2 of each other, and it's very easy to see this immediately in a metric space. Okay? Absolutely. So
then they might not be part of the real tree.
They might not be part of
the real set of points, right?
But the sample points, there is an underlying metric space. So I'm allowed to use any intermediate vertex as long as it's part of the metric space. This is why it's a Steiner tree. Does the algorithm make sense? Okay, let's analyze its cost. My claim is that the expected cost of my algorithm is no more than twice the MST. Okay? It's a simple enough algorithm. There are 3 steps to this. So let's look at the cost of each step. First, I take samples. Samples that don't cost me anything. Secondly, I build a spanning tree, the minimum spanning tree, on the samples. The minimum spanning tree on the samples is equal to the minimum spanning tree on the real points in expectation. They're from the same distributions, right? Good. First 2 steps gone, the third step comes in. So this is where I'll have to do a little bit of work, but the pain is bounded. The proof is only this long. Okay. Let's look at the cost of the ith real point. How much does it pay? Well, it's at most the distance from the ith real point to the samples. Okay? which is at most the distance of the ith real point to all but the ith sample. This S minus I just means S1, S2, Si minus 1, Si plus 1, whatever. Okay? But the ith real point has the same distribution as the ith sample. Okay? Good. So, the total expected cost of the real points is at most the sum of distances from every sample point to all the other sample points. And then now I can ask you, in a minimum spanning tree, if you sum up the distances from every vertex to its closest other vertex, this is at most the cost of the minimum spanning tree. That's it. So the cost, the expected, forget the expectation, the distance of Si to all the other sample points is at most, summed over all I, is at most this minimum spanning tree of S. Did it make sense? Yeah. Good. So, here we were using the bare minimum. Could you do much better? So you can, and you can improve it by a little bit. But, I don't know how to improve it by, let's say, a huge amount. I don't know how to get, let's say, 1.1 out there. So. Yes?
So distributions are independent.
I forgot to mention that. Thank you for pointing that out. Here I'm crucially using, in fact, previously also I was crucially using that the distributions are independent. And in fact, that leads me to the first direction that we should understand better. What happens when there are correlations between distributions? It's because we need to quantify the correlation. If they're arbitrarily correlated, it's the worst case. So what happens, let's say they are drawn from some Bayesian model, or they are k-wise independent. There are some partial results on that, but not very much is known. Thank you. Yeah, one more question.
In this kind of analysis, do you care about variance?
Do we care about variance? In this, no, we don't, but we should. Another question, number 2. From now on, keep asking the questions, and I'll tell you they're open questions or not. But in this case, we haven't looked at them. I mean, the traditional analyses don't look at them, but we should. Typically, the variance bounds are not very strong. You can show that they necessarily tend to be weak. Yes, please.
What if we assume like the previous talk has adversaries there,
Uh-huh.
but maybe don't have maximum power, so maybe they can do k bad things to you. Not too much.
Mm-hmm.
Because if they do too much, then they are back to the road.
Absolutely.
How bad?
So I don't know the answer to your question right now, but if you wait for another 15 minutes, I'll tell you about a different model where we do something like that. There's one more question, yeah.
If the distributions are independent,
Uh-huh.
there's a chance that when you sample that you will have a collision and then they'll be fewer than n samples.
Right. But it doesn't matter for this analysis. Yeah. The linearity of expectations makes it work out. It's fine. Okay. So I just showed you for Steiner tree, a factor of 2, or actually it should be 4 for the profit model. I'm going slower than I wanted to, but let me tell you this one, and then we'll take a 2-minute break. Actually, you know what? How long do I have, Devesh? Okay. So let's do this. Let's do this one, and then we'll take a break. Okay. So what I want to do now is I want to show you something for set cover in the secretary setting. Okay. So what's set cover? I give you an element, you have to pick a set. You have to make sure that this element is covered. So this element came, you pick the red set. This element came, you pick this set. This element came, hey, it's already covered. You don't need to do anything with it. Already covered, locked out. Need a set, already covered. Okay. So I pick 3 sets. I can compare to the optimum. In this case, the optimum actually happens to be 3 as well. So we just lucked out. Okay. Okay. So here's an abstract way of looking at it. I just want to make sure the model is clear to you. Okay. So what's an abstract way? They're sets. An element comes, and it shows you which sets it belongs to. You have to make sure one of its neighboring sets is picked, because those are the sets that cover that element. This element comes, it picks this set. This element comes, hey, one of its neighbors is already picked. No, nothing to worry about, and so on and so forth. Okay? Okay. What was the adversary doing? The adversary was picking the sets, the elements, which element belongs to which set. And then it was exposing the elements one by one, and you were picking sets on the left-hand side. Okay? For the random order model, what happens is, ignore all this. Here's what the adversary does. The adversary fixes this structure. But now, of course, it doesn't show it to us. This structure is revealed in random order. Maybe V1 comes first, then V4, and so on and so forth. Right? The elements are coming in random order. And the question is, can you do better than the sort of worst case analysis? Now, maybe I'll just mention out here that in the worst case, I should go to the previous slide. In the worst case, the comparative ratios look like log m, log n, where m is the number of sets, n is the number of elements. In the online setting. In the offline setting, there was just one log. So there was a gap between the offline and the online, and we wanted to close this gap. So let me tell you about an algorithm that will do it. And I'll tell you an algorithm, and a sort of simple algorithmic principle, right? Under some assumptions. And then I'll indicate how to remove these assumptions, but it's not important. Okay. So I'm going to give you an algorithm for the case where the sets cost me 1. In general, you can have cost on the sets. All sets cost 1. Good. Secondly, I'll allow my algorithm to take exponential time. I don't like it, we'll improve it, but I don't, right now, exponential time. Okay? Thirdly, let's even say I know the number of sets that optimum picks. That opt picks k sets. I don't know which k sets, but opt picks k sets. A little birdie told me this. An important algorithm design principle. The little birdie principle. What if a little birdie told you a piece of information? Can you do better? That's what we do. Okay. We know opt picks k sets. Okay? Good. So I'm going to give you an algorithm which is going to run in this model, in this exponential time thing, and then we'll improve it. Okay. So here's what's going to happen. There are m sets overall. Opt contains k sets, right? How many possible solutions are there? How many candidate solutions are there? M choose k. Fair enough? So there's going to be a box which is going to contain all possible k sets out of m. M choose k. I think of these as, hands, where a card is a set. Okay? Good. Suppose I could halve the number of candidate solutions every time. how much time would it take to come down to one solution? K log m. K is opt. So opt log m. That would be great. We would be very happy. Single log. Okay? Good. That's what we'll try to do. Secondly, there are n elements that I have to cover. Okay? I don't know what these elements are, but there are n elements I have to cover. Suppose I were to pick a random set from opt. What fraction of these n elements would I cover? 1 over k. So if I was picking sets randomly from opt, I would reduce the size from n to n times 1 minus 1 over k, to n times 1 minus 1 over k squared. How many times would I have to do this before I cover all the elements? K log n. Okay? So if I can reduce the number of uncovered elements fast enough, I'd make progress. If I reduce the size of my search space by half every time, I would be very happy. Okay. So here's what I do. I'm going to maintain some solution on the side. When a random element arrives, if this element is already covered, nothing to do. If not, pick a random collection from the collections I already have. Pick a random set from that collection. Okay? Furthermore, from those collections, throw away all, from that collection of candidate solutions, throw away any candidate solution that doesn't cover this element that just came in. This kind of makes sense? Those solutions can't be a solution, can't be the optimal solution. Okay. And then finally, I picked a random set from a random collection that might not have covered that element that I wanted to cover, so maybe pick another set that covers it. Okay. And that's it. I repeat this process. So maybe I'll show you another one. Okay. This yellow element came in. All those sets, or all those candidate solutions covered the first two elements, maybe not the third one. You picked a random hand from this collection, picked a random set from there, and then threw away all collections that did not cover this new element. Okay? What's the main idea? So the question we ask is, you have some collection in your hand. You have that collection out there. Are half of the remaining solutions good, as in they cover at least half of the remaining elements? Suppose half of the solutions are good. If half of the solutions are good, then with probability 1/2, the random set I pick contains a lot of uncovered elements. Call a collection good if it covers half the remaining elements. Okay? Half of the collections are good. So if I pick a random collection, it's good with probability 1/2. It's good, meaning it covers at least half of the remaining elements. So a random set from that will cover 1 over 2k of the remaining elements. I've reduced the number of remaining elements by a lot. Okay? In the other case, half of the remaining solutions are crappy. Then if I pick a random element, it will not belong to half of those collections. I'll throw away half of the collections in my hand. I'll make progress. Either I cover a lot of remaining elements, or I learn a lot about the collection of sets. And if you, oops, I seem to have pressed, okay. If you do the calculation and it's kind of late in the afternoon, don't worry about it. I'll put the slides online. You will either reduce the set of candidate solutions by half every time. It's not half, it's a constant factor, but we lose constants. Either you reduce the number of candidate solutions by a constant factor every time, or you reduce the number of uncovered elements by a 1 over constant times k every time. You either learn something about the optimal solution, or you cover a lot of uncovered elements. And the design principle perhaps I want to mention out here is, well, if you have a collection of possible solutions and you can halve it every time, there's only so many times you can do it. The missing ingredient was, if you can't make progress halving the number of candidate solutions, you want to show that you are making good progress covering uncovered elements, which is what we did. If you want to make this effective, you want to make this efficient, you can't store all these m choose k solutions. What do? Well, maybe you use my favorite algorithm, which Ria is smiling out there. I taught advanced algorithms, and then in every lecture I would say, well, this is my favorite algorithm. And the students would refuse to believe me. But this is really my favorite algorithm. My favorite algorithm is the multiplicative weights algorithm. So I'll spare you the details out here. You use multiplicative weights, you write down a potential function, and you show that it works. And let me not do the gory details out here. Let me just mention that using this, we can get a single log in the random order model for set cover. And I'm sorry I lost several of you in the details out here. The algorithm is dirt simple. So catch me again, and I'll tell you. I'll repeat it. Hopefully you'll understand it much more cleanly next time. Okay. Let me take a 2-minute break out here and see if there are questions. Otherwise, I'll tell you a model to interpolate between the average case and the worst case, and then we'll stop, because there's only so many models that one can see in the afternoon, so late in the afternoon. Questions? Yes.
Is there national motivation from the random order?
Good. So the motivation I came to this model because of was that I wanted to understand. Remember, in the profit model, I assumed I knew the distributions. What if the distributions were identical, but I don't know the distribution? And then this naturally leads to an exchangeable sequencer. It gives you a random order thing. And then we found out, then we realized that this is the same as the secretary problem. The people who were studying these were probabilists, and they were just interested in this model by itself. But I think it's a first step. I always think of this as a first step towards understanding the power of the ordering in these inputs. So the question was, in the algorithm I gave, I needed to know k, and I can give you one other very simple but very powerful idea: guess and double. So let's guess that k equals 1 and run the algorithm. And if the algorithm fails, just run the algorithm.
Like what you usually do is you guess k, you grain it nicely, and then you run it in parallel, and one of them will finish.
So in fact, don't run it in parallel, run it in series. Imagine k is 1. And you keep running it until you have a proof that k is not 1, k is more than 1. Now k is 2. So you paid 1 log n plus 2 log n plus 4 log n plus 8 log n, k log n, 2k log n. Exactly. Guess and double is a very useful idea out here. Other questions? Okay. So let me tell you this final bit, and then we'll stop. So what's this final bit? I want to talk about a model which interpolates between the average case and the worst case. Okay. So we saw, you've seen this this line earlier, except So the worst case, very robust, conservative, pessimistic. The carefully chosen data models, you get very strong results, but often it's a little optimistic. And really the problem is we come up with an algorithm for a data model. Right? We fix the data model and then get an algorithm for it. And then the question we should ask is, are these algorithms good when the data model is not quite right? Good. So let's follow this chain of reasoning a little further. So the question we ask is, okay, I want to do just max k finding. I want to pick k elements, maximize their sum. Okay? But the model is slightly more nuanced right now. It's drawn from some model, but then the adversary corrupts it in some way. Suppose here's what's going to happen. Actually, let me even skip over this thing. The adversary chooses the values of all n elements. Okay? Some of these, just for the adversary's convenience, are green, good elements, and some of these are red, bad elements. You'll see what good and bad are in a moment. It fixes the values of all the elements. In the secretary model, these n elements would appear in random order. Okay. Here, things are a little different. The red elements appear at specific places. And just for concreteness, I'm imagining that time is between 0 and 1. And every element appears at a time. So what the adversary does is it fixes the times of all the red elements. The green elements appear at random times. Okay? So if every element were green, this is the secretary model. If every element were red, this is the worst case model. So this is like a partial, it's a semi-random model, if you will. Okay? What can we hope to get? That's the question. Okay? Of course, we don't see the colors. If we saw the colors, we would, whatever. Okay. What we do want to do is we want to get pretty much the sum of the green values, because the red values are worst case. We can't hope to compare it against the red values. We want to do as well as the top k green values, let's say. Can we do it? Fair enough? Okay. So more or less, okay. And here, you should think of what was the algorithm that we used just for the secretary problem. The secretary problem, we said, wait until halftime, look at the maximum element in the first half, set that as a threshold for the second half. Is this algorithm good when the adversary can, fix certain values to come at certain times? No, because it can give a very high value right at the beginning. It can give a very high value right at the beginning. You'll set a high threshold, and nobody will be as high as that threshold. Okay? Good. However, you can still do something algorithmically. And maybe I'll just mention the idea here. What's the idea? Okay, what's the theorem? Okay, the theorem says if I am picking at least some number of elements, I need some room to make mistakes. So as long as I'm picking enough elements, then I can compete with opt. I need some technical conditions. Let me give you the punchline. The punchline is I'm going to get a algorithm which I call a single parameter algorithm. And this algorithm will be robust to adding red elements. Okay? And again, this is the little birdie principle. If somebody told me the right value of this parameter, I'd have a great algorithm. I don't know the right value of the parameter, but I can learn it. That's the main idea. Okay? And remember, I want to pick k elements to maximize the sum of the values. Suppose the green values are g1 through gn. I want to pick a threshold. Suppose you said, tell me a threshold so that if I pick elements above this threshold, I'll get good value, even if I inject red elements into it. Okay? If you've if you had lost me earlier, let me ask the following question. There are n green elements. I can inject as many red elements as I want. Okay? What's a threshold? And the only algorithm I'll allow you is a threshold-based algorithm. You'll pick the first k elements which are larger than this threshold. Okay? You want to get large value. Okay. So what would you do? You can say, well, let me pick the kth green item, the value of the kth green item as the threshold. You would get value g1 plus g2 plus g3 up to gk. Okay? This is a great algorithm. But if I'm allowed to inject spurious items into this sequence, can I make you get much less? And the claim is, indeed, I can, because what I can do is I can, imagine the situation where all the greens except the kth green are very large. So G1 plus G2 and all those guys are very large. GK is very small. The sum of those guys is very large, but I can give you a lot of red elements which have very low value. And so you would get only this plus this plus this, whereas opt was this plus those two high guys. So if you knew, if you knew the value of the kth largest item, it's not very good. However, there's a different threshold you could set. It's, if you think about it for 2 minutes, you can set a threshold equal to half the average. If you take half the average, the number of the total value you lose is at most half the average times k, which is half the total value. So if you pick all the elements above half the average, you're getting a good value. So if you knew the average value, you'd be in great shape. You don't know the average value, so you learn it. How do you learn it? You use online learning, and maybe that's where I'll stop. So let me just stop here and mention that I just want to recap where we were. So what were we doing? We said we want to go beyond the worst case analysis in general. So we should look at maybe more nuanced models. If we look at more nuanced models, we can come up with a variety of models. One of them is they're distributional models. There are semi-random models. There are models where we assume that the graph is nice, or or the data is low dimensional. All these are beyond worst case models. And in this talk today, we saw a bunch of examples where we used distributional assumptions. And then finally, we stopped with trying to say, look, you might not want to make either a very strong distributional assumption or a very pessimistic worst case assumption, but something in the middle. So make a distributional assumption, but the adversary is allowed to corrupt a little bit. And what can we get in that case? And there's a final direction that people have been looking at, which is using predictions. So your algorithm is given some predictions on the side. It's like a little birdie can tell you a lot of information, but that information can be very wrong. So how do you handle that situation? But maybe I'll save that for another day. There's various, there's a lot of open questions out here that you might be interested in. In general, the sort of difficult questions, maybe I'll mention two of them. One of them we already talked about. Many of these distributional assumptions critically use independence. What happens if there's dependence in the data? And another one is how, so in these sort of distributional models, very often the robustness question is almost never addressed. That if I gave you a distribution and your distribution is close but not exactly the distribution from which the data is being drawn, how well does your algorithm do? And quantifying that is a very important direction that I think we should look at. Maybe I'll mention a final third direction, which is in a lot of our algorithms with predictions, we don't talk about how we learn the predictions. So we should talk about the sample complexity of learning those predictions and try to prove sort of trade-off results of how well we can do along the lines of the question you asked, Reza, that if these distributions, I took one sample each and I got this kind of behavior, what if I took many samples? Can I improve the behavior? So the sample complexity is, again, very poorly understood right now. And one issue why that comes up is, anyways, let me stop there. Thank you all.
Are there more questions? Yes, Roland.
Oh, cool.
Maybe this is quite a sideways question, but there are some problems where if you knew the particular class, could get a very efficient algorithm. But sometimes to know if the thing is in a particular class itself is a hard problem. So if you knew this was in that class, it's easy problem. But to know what is in that class is unfortunately a hard problem. So it's the characterization of the class. It's kind of, it's like, sometimes it goes under meta problems.
Yeah. No, I was trying to think of.
Just wondering whether that can apply in this setting. Maybe not, because those tend to happen in more NP-type settings.
Yeah. I don't have a concrete place where it can help, but I'm happy to chat more and figure out whether something interesting can be said out there. Yeah.
The last problem you discussed, was it still in the online setting? Because I can't imagine how you might learn the average in a robust manner, because the adversary can pick when the red points appear in the online setting.
Good. So one thing, the way we learn it in a robust fashion is basically we sort of take, because the adversary is fixing the position of the red points and is not changing it adaptively. So the model said the adversary fixes the position of the red points, then the green points come in random order. So if you take time and you break it into pieces, then the first half, let's say, will have a reasonably good estimate. Now, if the adversary could start changing the later positions based on the earlier ones, I don't know how to handle that. So that's a very valid concern.
I guess there were enough questions
Cool.
during the talk.
Yeah.